Hi. This is not prepared, by the way. I'm muting my phone. If you want to do the same, feel free. Let's see. So yes, my name is Magnus, or Magnus in Icelandic. For those of you that are Icelandic here, which I'm guessing not that many. I would like to thank Ryan and his friends at Facebook for actually hosting this. This is a phenomenal job they're doing. And it's nice to be able to talk to the community about some of the cool stuff that we're doing at Oracle Endeca. Now, I'm biased, of course. I think it's really cool. Now, when I say we, who is this we? I'm from Oracle. I'm from a team within Oracle called Endeca. It's actually a company that was acquired by Oracle about 3 years ago. It's a company founded 15 years ago and became kind of the 800-pound gorilla in the e-commerce marketplace, all on the basis of a pretty novel columnar in-memory data store. That's kind of a hybrid between a database and a text search engine. It was actually so popular that the company was logically split in half. One half continued to pay the bills. The other half was tasked with conquering BI. And that's the piece where I'm from. This is a very high-level overview of this engine, this data store. As you can see, it has the 4 basic components. You have an API. You have a query language, which we call the Endeca query language. It's basically SQL. If you know SQL, you know equal. It has Eve, which stands for the Endeca virtualization engine. I think we've now managed to cram every single buzzword into this slide. You have virtualization, you have columnizing, lock-free updates, snapshot isolation for read queries. So it's a pretty neat thing, if I may say so myself. And at the bottom there, we have this generational data layer, which is responsible for storing all the indices, all the data. So I want to talk about query evaluation. What is query evaluation? I don't know how many of you understand or know in detail about the intricacies of evaluating queries. So I put a somewhat simplified overview of the main 4 phases of query evaluation. The first phase is the parsing phase. That's where you take the language, the SQL or the equal, and you translate it into a representation that you can actually manipulate programmatically. A high-level AST, an abstract syntax tree. The second phase is the optimization phase. You take that syntax tree and you figure out, well, if I would order it this way, would take this join and put it over here, it would run faster. Or the AST would be simpler. Then you take that AST and you think, okay, this is a high-level description of what the user wants to do. Now I want to translate that into something that I can actually evaluate, because the evaluation primitives are different from what the user specifies. That's the third phase, changing that into a planned language. And then the last piece is to actually execute that part. And that's the piece that I'm going to talk about more specifically, the code generation of that piece. So here we have an example. By the way, this is, I was Googling around yesterday for a good set of images to kind of give an example of what these phases look like. And I hope, if Pat is in the audience, Pat Shaughnessy, I hope you don't mind that I borrowed your pictures. This is actually, I should note that this is an example, kind of a walkthrough that he did for Postgres. So it's not actually showing our product, but it's kind of a Postgres overview. But it does show at a high level, the different, the difference between those 4 phases. So the first part is the SQL statement. So it's pretty simple. Get me all the data from a table called users, where name is equal to Captain Nemo. I want to order it by the ID, and I want to take kind of the first entry. That's translated into an AST that looks something like this. So this is the Postgres AST. As you can see, that this really is a way to represent the original query, but kind of broken down into components. This is a simple query, so there's not a lot to optimize. But the last phase is now translating this into an execution plan. Now, the execution plan is based on these primitives of let's scan sequentially over the data, let's gather all the results, let's sort them, and let's take the limit that's specified, in this case 1, basically the top hit from that table. Simple, right? Now, if you want to build an evaluator to evaluate this, you would do it in a general purpose way. So it would handle basically all the different types of node and all the different types of types that are being worked with, whether it's string or integers. And a lot of times it means that you end up with an evaluator that's general purpose, with virtual functions about this big, with a bunch of different switch statements depending on which kind of types you're working with. And that adds overhead. So wouldn't it be nice if we could actually take a really good developer, put him into a box, somewhat like a Mechanical Turk, and tell him, you know, write an evaluator, but just for this query. How much faster would that evaluator be compared to the general purpose evaluator? I mean, it's a good idea, but it really wouldn't scale beyond maybe a few boxes, after which you kind of run out of good developers. And I'm not sure they would actually like being stuck in a box, being asked to generate evaluators for very specific queries. So a better idea is actually to use code generation. Basically write code that writes code. So you would write a code that would write an evaluator just to evaluate this specific query. And if the query was different, it would create a different evaluator for that query. So what are some of the pros and cons? Well, hopefully you would get faster code. There's no virtual function overhead, there's no type switching. You can do fancy things like loop unrolling, and typically it would result in a code that's smaller, more compact, not kind of jumping all over the place, which means that it is much more CPU cache friendly. The inner loops would most likely possibly fit into the instruction cache. The entire evaluation may fit into the L1 cache. It would automate repetitive tasks, which means you would basically end up with more maintainable code. We actually had a guy who printed our old evaluator. He kind of printed it in a bunch of letter sheets, glued them all together, rolled them up, and had this very compelling demo. He would say, so this is the old evaluator. He would roll it, it would stretch out like 20 feet, and then would compare to the prototype code for that same evaluator using CodeGen, which was like this big. And if you want to ask him more about it, he's actually that guy over there who is giving the next talk after. Another pro is that it gives flexibility in implementing different types of operations. So you know the query, you know the data, and different operators could be implemented in more efficient ways, knowing that in advance. Now, cons. What are some of the cons? Well, there's overhead, right? You actually, instead of having this pre-compiled general purpose query evaluator, you actually have to create the evaluator at runtime. So you have to build it, you have to compile it, you have to link it, you have to run it. So that's actually like something that goes into the budget that you have for evaluating the entire query. So that's definitely overhead. The second piece is that writing code that writes code is more complex. So it may mean that the code is less readable, maybe less maintainable. Now, in this exercise, in the prototype that we did earlier, we kind of took the first step of saying, well, let's build the code kind of that spits out C++, full C++. And then we compile that, and then we run that, and we link. That's kind of everybody that does code generation would kind of start with that. But this was about 2 or 3 years ago, and we ran into a tool called LLVM. I don't know how many of you have heard of LLVM or know LLVM. Okay, so maybe 1/5 or so. So LLVM originally stood for low-level virtual machine. It doesn't really apply now, so I think they deprecated that. Now it's just LLVM. It's really a compiler toolkit. And the way it's done is that they say, well, our intermediate representation is king. So if you have your languages, C++, C, Haskell, Fortran, whatever, we build a way, or we provide a way to take your code and compile it into IR. Then we do all the optimizations and all the analysis in the IR itself. And then we have a different set of tools that take that IR and compile it into backends, whether that is x86 or ARM or PowerPC. And I can neither deny or confirm that Oracle may be working on a Spark backend, maybe. Some of you may know that, so Oracle bought Sun, and Sun is a big advocate of Spark. And there may be some very cool Spark things coming out soon, but maybe. So what is this IR? IR stands for intermediate representation. It's basically a low-level programming language that's very similar to assembly, somewhat idealized assembly with infinite set of temporaries. The goal with the IR is to make it easy to produce and easy to understand. And mostly language and target independent. I mean, there are some peculiarities of certain targets that have to kind of be reflected in the language itself, but the goal is to be as independent from the target and the language as possible. And of course, having one IR for analysis and optimization make things nicer. So if you're doing these optimizations, you have one language you work with, and that is IR. Here you have an example. So this is a very simple function in C++, does multiplication and addition. And below there, you can actually see the IR representation of this function. If I say so myself, it's actually quite readable. You have the return type, defined function, and you have temporaries, an infinite set of temporaries. Okay, so this is kind of the meat of the talk. This is how we use LLVM. And there are a few interesting things here. So we start with the SQL-like query. We do a query rewrite. We transform it into the AST query representation. Then we do algebraic and cost-based optimizations on that AST. Now, the Eve piece, the Endeca virtualization engine that I talked about, it's basically a relational algebra. So we can do a lot of optimization based on algebraic properties of the AST. So once that optimization is done, we actually plan the execution and we do the partitioning. So the partitioning is necessary because we are data parallel. So as we look at the plan, we think about how can we execute this plan in as a parallel fashion as possible. So we partition the execution so that each piece works with each set of each portion of the data. At that point, we end up with an optimized execution plan. What we do then is that we actually compile that into IR. And this is a very important point. The original prototype showed us that compiling into C++ makes the runtime overhead of CodeGen quite expensive, because now you're compiling this full-fledged C++ program into machine code. So what the path we took with LLVM is that we said, well, let's abstract any algorithm, any general purpose algorithms. Let's actually pre-build the IR for those algorithms. And let's, at runtime, only generate the pieces that are type specific. So we have the dynamically generated IR on this side, and we have the kind of statically pre-built IR on that side. And then at runtime, we do the linking. And LLVM is smart enough that it actually does the inlining automatically. So what we end up with the full LLVM IR, which we then optimize to end up with optimized IR, which we then compile into machine code. And of course, we run it. Now, I should point out that we do caching on many of those steps. So if you have a query, the same query as before, we actually cache, well, first we cache the plan, and then we cache the IR itself. So you don't have to pay the overhead for every single query. We actually try to be smart enough. We actually try to parameterize the caching itself. So if it's similar, we can actually leverage the pieces from previous runs. OK, so here's an example. So this is actually from TPC-H, if I remember correctly. And I want to focus on that select condition. So basically, it's saying the ship date has to be 90 days before 1998, December 1st. Okay, so this is the query condition. In the plan language, this is what it would look like. This is our plan language. So what is it doing here? It's basically saying, run this row expression on a corpus called ship date. And then it says ship date is actually, it's an index, a forward index, that's what the F stands for, of 64-bit integers. Go over that corpus, and for each value, run that expression. And it's basically saying, so the n, n10s and n12 are just node numbers. And then you have the type, so this is Boolean. But basically see if the entry, the integer entry in column 10, is less than that constant. So this is the IR, this is the plan language that we generate, which then gets translated to LLVM IR that looks like this. The fetch value function is the function that's pre-compiled to actually get the value from the corpus. And finally, this is the machine code. So this is pretty optimal. So this is the actual code that runs, no virtual function overhead, no type switching, that's it. So is it worthwhile? I mean, did it make sense? Did we gain after all of this exercise, right? That's the big question that everybody must be asking. And here I have results from an internal benchmark. So this is based on TPC-H. And in bright red, you can see the old evaluator. On the dark burgundy, I guess is the color name, is the new CG-based evaluator. And as you can see, by the way, this time includes the code generation time. The code generation time with this approach was between 1 and at maximum 10% of the total evaluation time. And as you can see, the benefits go from 1.6 to 7.5 times faster. So for us, it was quite a win. And that's my spiel. Any questions or thoughts? It's still kind of early, I know. By the way, thank you so much for having this at a reasonable time, not something godforsaken like 8 a.m. Yes?
Why does the speed up vary as much as it does? What does it depend on in the query itself?
Do you want to just repeat the question? Yes, that's a good. So the question was, why is this varying thing? Why does the performance vary? Why is it sometimes factor of 2 and sometimes factor of 7? It's basically the makeup of the query itself. Some queries benefit more from code generation because they have more virtual function overhead that we manage to shrink down. Others have a more kind of unnaturally simpler and therefore do not pay that overhead in the old legacy static evaluator. You had another question?
Yeah, can you make can you characterize whether this is worth doing it based on the size of the data that you expect to come out of it? So obviously, if you kind of gear up for the big game here, you go through this whole compilation thing, that's really going to only do one table scan of a small table and produce one row as a result. It was kind of overkill to do all that code generation. Right?
Yes.
Do you try to optimize that out, or have you thought about that?
We haven't yet. We've talked about it. It does make sense to say that we basically have if we look at the query and we say the overhead of code gen is not worthwhile, therefore let's fall back to the old. We could have, we decided not to for just maintainability of having one evaluator, but that's absolutely something we could have considered. Yes, you have a question at the back? Yes. Go ahead.
So on the rightmost one there, where you achieved 7.5 times improvement, can a programmer do better? Like, is 7.5 the best it can be, or could it be 8x if you in starting the project, you obviously had goals. Did you exceed your goals, or did you just meet them?
We exceeded our goals. The prototype that we did was slightly better, but not significantly. So with these kinds of numbers, we definitely exceeded our goals. Can a programmer do better? That's a good question. Probably, if he's really good. but that would be a multi-month undertaking for a single programmer optimizing that single query. So is it worthwhile in terms of cost-benefit analysis? Probably not. Probably not.
So these were queries against an in-memory database. These are, what can you say about these queries? Because it seems like, certainly if you're I/O bound, if you're waiting for the disk, this wouldn't show
This
up.
is all in memory. Yes. So the question was, are these queries against an in-memory bound database? Yes, it is. This is all in memory. So the Endeca server, or the dgraph, the MDEX, it actually memory maps all the indices. And at this point, the OS cache is hot, so we can consider it to be in memory. We're kind of out of time. If you have further questions, feel free to catch me after the talks. Thank you.